Hey everybody, this is Professor Ross here to talk about fraction addition and subtraction. So we've talked about addition and subtraction before with whole numbers. How are things the same and how are things different with fractions? There are actually a lot of things that are very similar in our approach to teaching addition and subtraction with fractions as they are with whole numbers. For example, we talked about there being value in allowing students to invent strategies before coming to a traditional algorithm with whole numbers. Similar kind of thing with fractions. It's good for students to explore how they might solve a problem before we've tried to show them the traditional algorithm. Uh, Ultimately, we'd like to get them to the traditional algorithm, but when we build on a basis of understanding for them, it's more meaningful for them and they can actually make sense of and remember the traditional algorithm better then. Also, we've talked about working in ways to make connections to meaning with whole numbers. We also want to make connections to meaning with fractions. So it's very important to understand what the whole is, what the denominator means, what the numerator means. All those things are going to be important as we talk about adding and subtracting fractions. We also want to have students use a variety of models, and we talked about using models and the value of that with whole number computation. Also very, very valuable with fractions. Models like area models, linear models, set models, trying to get students to think about problems with all those different models, and context that makes sense with the models is a valuable thing. And finally, with whole numbers, we talked about a variety of structures: join, separate, part, whole, compare. We also want to use those same structures to get students to think about addition and subtraction with fractions. There's not really much difference there. We can have problems that are join problems with the result unknown, and they need to add two things, and in the case it'll just be two fractions. I'll do a problem like that, but just so that we can easily make a join problem with the initial unknown, and then it would be a subtraction problem. And students should see a variety of all these structures and unknowns so that they're doing addition and subtraction in a variety of settings. Let's talk about an example. So let's say we had this problem here. Finch can eat 1/3 of a pie. Reese can eat 1/4 of a pie. How much of a pie can they eat together? So once again, we're joining two things, the amount of pie Finch can eat, the amount of pie Reese can eat, and we're trying to find the result. So this is going to be an addition problem. Traditional algorithm says take 1/3 plus 1/4, and find the common denominator, right? So multiply these by 4 and get 4/12. Multiply these by 3 and get 3/12. And then add the numerators, but not the denominators. And there's our answer, 7/12. There's a lot there for students to get confused by or be mysterious. We've talked about this process of creating equivalent fractions, and if students don't understand how that works, they can get confused. We've talked about the importance of common denominators in fraction comparison and equivalence, and so it plays another important role here, but if they don't understand why, then they're just like, oh, I guess I need a common denominator. And then there's also this idea of why I do addition with the numerators but not the denominators. And if they don't have any sense of what's going on, that's all going to be very confusing. It'll be very easy for them to mix these things up. Like one of the common things for students to do is add 4 plus 3 to get 7, add 12 plus 12 to get 24, and have 7/24. If students have a little bit of understanding of what's going on, they might quickly realize like, oh, 7/24 is actually smaller than my original fractions, and that's problematic. But we want them to have a good understanding of everything all the way through, so that they aren't prone to those kinds of mistakes. So how can we build understanding? A lot of times looking at visuals and thinking about that can be helpful. So let's think about this. Finch can eat 1/3 of a pie. What does that mean? Well, 1/3 means I'm taking a pie and I'm cutting it into 3 equal parts, and one of those here is what Finch can eat. I'm going to label it with an F here for Finch. Reese can eat 1/4 of a pie. That means I would take the pie and cut it into 4 equal pieces, and then 1/4 of it would be Reese. Now, that's I've already cut it into 3 equal pieces. cutting it into 4 equal pieces isn't very intuitive here, because if I tried to overlay that, right, it wouldn't really line up with what I've got going on here. So this is the challenge that we face with adding fractions, is sometimes these pieces are not the same size. We could maybe try to estimate, put some kind of guess in here about what Reese has. But just from looking at a picture, it'd be hard to say, is it exactly half? Is it a little more than half? It's a little bit hard to say just from a picture. So we need to try to come to some kind of realization of how we can figure out how to get these two fractions going on the same whole. And as I suggested in the last video, how important the idea of a common denominator is, cutting these into the same size pieces. That ends up being the key with fraction addition and subtraction. So it's something that hopefully you've laid a lot of groundwork for students, that they're thinking about, can I get these pieces in the same size? And here, how can I get fourths and thirds in the same size? Well, I might have to think about taking these 3 things and cutting them into 4 pieces each. So cutting them in half, and then in half again, and cutting this one in half and in half again, and cutting this one in half and then in half again. And now I've got a place where I can think about how 3 of these together would make 1/4 of my pie, because I've got 4 groups of 3 of them. And so Finch is eating 4 of these slices here, and Reese could eat 3 of them. We'll put a R here for Reese. And so all together, how much are they eating? 1, 2, 3, 4, 5, 6, 7 pieces. How big are my pieces? Well, if I count around the circle, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. I've cut it into 12 equal pieces, and together they can eat 7/12. We see it's the same result we got with the traditional algorithm. The key is for students to realize that they need to get these pieces cut into the same size before they can get those together. And guess what? That's exactly what the traditional algorithm does. It says, let's get common denominators, and then it's simply a matter of adding up the number of pieces we have. So getting students to think things through and realize the importance of common denominators is a great bridge towards the traditional algorithm, which they can then use for fraction addition and subtraction. It's pretty much the same algorithm, we just add or subtract the numerators. So those are our key ideas here for fraction addition and subtraction. Always trying to anchor things to meaning and strategies that they're thinking about themselves as we build towards a more algorithmic approach.